Welcome to the NewSpace India podcast, a bi-weekly talk show that exclusively captures insightful conversations with people contributing to advancement of space activities in India. The NewSpace India podcast is pleased to announce our association with Dassault Systems, a global leader in providing business and people with collaborative virtual environments to imagine sustainable innovations. Dassault Systems solutions support startups, small and medium-sized enterprises, and original equipment manufacturers in developing disruptive solutions for space launches and satellite propulsion. Recently, a supply chain digitization study with Dassault Systems was conducted to provide a foundational understanding of the supplier landscape in the Indian space ecosystem. Please use the link in the description to download the public white paper of the results of this study, which will also give you a perspective on how ready Indian suppliers are to enter the global space market. Welcome to this episode of the NewSpace India podcast. And here we have Dr. Ranganath Navalgund, who has spent a tremendous amount of time at ISRO. And he's going to talk to us about his career in ISRO and some of the insights around what's gone on with satellite remote sensing and geospatial analytics and so on with ISRO for the last 30 to 40 years. Welcome to the show, sir.
Thank you very much for this invitation, and it would be my pleasure to talk to you on my experiences of the last 40 years almost, since I joined in 1977.
You did talk about, you joining in 1977. So how did you occur? How did you know about ISRO then? And, what was your interest in space, or how did you land up in ISRO?
I think I must give a brief background to this. Obviously, I didn't know ISRO at all when I was in my high school or even college. I come from a district town called Dharwad in North Karnataka. And I had my early education there in Dharwad till the graduate degree, BSc in physics. Those days, I don't think I ever thought of any career related to space. I had general interest in space even then. That's because of the large number of lovely brochures which were being sent by USIS office in Chennai those days related to NASA missions. And that was the only thing that used to excite us, that there is something going on with respect to space technology. But I don't think I ever had any thought that I will have a career in space-related activities. Although I had opportunities to join any engineering colleges, for example, the Indian Institute of Science, Bangalore, after my graduation. Before that, the University Department of Chemical Technology at Bombay, but I didn't do. I went over to the Indian Institute of Technology, Bombay at Powai, for doing a postgraduate degree in physics, MSc Physics. And that's it. And after that, of course, I again went over to Tata Institute of Fundamental Research in Bombay itself. I joined in 1970, and I spent about 6.5 years, 7 years there obtaining my PhD. Now, after obtaining my PhD in physics, still I didn't have anything to do or any inkling of space, because generally, most of us who do PhDs in physics from Tata Institute of Fundamental Research go abroad for a postdoctoral fellowship. So I also had an opportunity to go over to Notre Dame University in Indiana, US. I had also an opportunity to go over to some academic institution in India to have a teaching job. But at the same time, I had this application coming from Space Application Center. I had not sent. They had sent me a form to fill up if I am interested. What happened was that I went to the US consulate in Bombay to get the visa to go over to US as an exchange visitor visa, they called. And the lady there, after talking to me, said, look, you are a very potential immigrant, so I will not immediately approve your visa. So I will have to get some kind of a understanding from you that you will come back, and maybe TIFR will give you a certificate or a letter saying that they will absorb you after you come back. I said, fine. So I waited for that. But in the meantime, this interview at the Space Application Center, I went over. And, it was a very small, it was an institution which was only 4 or 5 years old. And so I had no idea. But I knew there is something to do with remote sensing. So from my TIFR library, I took up a book which was on remote sensing, brought out by National Academy of Sciences of US, and just had some reading of that. The only thing that I understood was that you can identify and discriminate Earth's surface features if you use observations in different spectral bands. And if two objects look same in some 4 or 5 bands, then go for the 6th. This was what I had read or understood from that book. And so I went to the interview, and Professor Ishpal, who was originally in TIFR, was the founder director of SAC, and he was there with others. So perhaps they liked that I did do some efforts to understand what they are doing. So they selected me. By then, of course, the US consulate also had sent me the approval for the visa. But then that's it. I got stuck, and I remained I joined the Space Application Center. So that is how I joined the Space Application Center at Ahmedabad, which is a major center of ISRO. And this is just by accident. So my getting into the space activities is not in that sense any great plan, but by the fact that probably US consulate did push me into that direction by first refusing to entertain. So I think this is the circumstances when I joined the Space Application Center at Ahmedabad. I think this should give you a proper background of my joining the Space Application Center. And when you do your postgraduate degree, PhDs, etc., you're already closer to 30. So you need to settle down also. So you can't think of, although in the initial stages at SAC, I was not very comfortable because, although Space Application Center has many groups, there are people who are engaged in the development of electro-optical sensors, like led by Dr. George Joseph. There was a group led by Mr. Kalla, who was doing microwave-related sensors and development. There were other people who were developing satellite communication transponders. So there was a large number of hardware groups, Earth station groups were all there. But there was also a data processing group led by Mr. Kamath. But there was the group to which I was put was the one which was related to more use of data, which comes from remote sensing or satellites. How to use it, the more towards the applications of this. So that wasn't blue sky physics. I mean, it was not that. So I was a bit uncomfortable to start with. And this group had people, of different backgrounds. There were some who were agriculture scientists. There were some who were coming from geology background. There were some from plant physiology. There were some geography people. I mean, it was a mix of all, multidisciplinary team. So I felt a little out of place to start with. But then what happened was, as I mentioned to you, you are at an age where your choices, you cannot keep on hopping from one to the other. So I got stuck. I think that is how my journey in the Space Application Center began. Then, of course, I started taking interest. And at that time, the Space Application Center, although was very young, but the number of activities that it was taking up were very exciting. One of the activities was CO. That time it was called SEO. That is a satellite for Earth observation. This was an experimental satellite which was being built. One camera, Vidicon camera, and one microwave radiometer were built by SAC. And this was to be launched by the Russians. And so there was a lot of activity towards the investment of, to the pre-investment of how do we use this data which is going to come from this satellite. And parallelly, there was also another major program which was started by Professor Satish Dhawan at that time. that we should embark upon a full-fledged Indian remote sensing program. It was IRS. So that was the activity. There were a large number of activities towards that as well. So these were two activities which kept me very active. Since I had a slightly broader perspective than, nothing to, no reflection on anybody, my other colleagues who were probably had only a narrower background of a particular discipline, whereas I was not belonging to any of those disciplines. So I had a larger perspective of these things. So Professor Dhawan was saying that maybe we will build satellites, maybe we will build Earth stations, but what will happen to the data which comes? Unless this data is used by the stakeholders, users in the country, this cannot be the ultimate aim of only technology development. So he was very much interested in ensuring that there is a large infrastructure in the country which uses the data, and that too for purposes which are required by the country. So that is how I got very much involved in the so-called IRS utilization program. There are two important things that were there at that time. This was in 1979, just 2 years after I joined. One was called the Joint Experiments Program. What was it? It was an experiment which you have to do with users on what they want, whether it is agriculture, drinking water, watershed, or fisheries, and show to them that this data from remote sensing is actually useful from end to end. And if you want to do that thing, what kind of a satellite data is required? So these were the experiments which we were doing. The second was actually called end-to-end experiments. So right from the data which is received from the satellite to the end, to the final use of that data on the ground, you have to demonstrate. So these were the experiments for which I was the convener, some of those experiments. So this is what brought me into the main frame of utilization program. And all these experiments which we did, we also used them to define what kind of a satellite do we require. See, already Landsat was there. Landsat data was available. But is that what satisfies us, or is it something different from Landsat that we should have for our IRS program? So these were the questions for which you have to see what kind of spectral band should be there, what kind of resolution should be there, spatial resolution. So all these aspects, what kind of radiometry should be there, how should the data be there? So all these questions were very exciting as far as I was concerned. So all these things which were happening with respect to the joint experiments program, end-to-end experiments, etc., getting hold of users, all these things led to a major national conference, and that is called the National Natural Resources Management System Conference. That was held in 1983. And many secretaries to Government of India, Secretary Agriculture, Secretary Water Resources, Rural Development, Science and Technology, were all there along with Professor M.G.K. Menon, who I think was in either Vice Chairman, Planning Commission or something, along with Professor Dhawan. So all these people were there. That means there was some tacit understanding that the final stakeholders of this data are going to be using this data. That's why we are doing this program. So on the basis of this, that Planning Commission was finally given the responsibility to have this NNRMS. So NNRMS was set up under the Planning Commission. At the same time, Professor Dhawan saw to it that there are some standing committees. What are the standing committees? Standing committee, each is chaired by the secretary of a particular user ministry. Secretary Agriculture, for example, is the committee on agriculture. So what it means is, and there are people from states, there are people from space department, there are people from others, etc. All of them together will decide what kind of applications will you do with this data which is likely to be available, and you will work for it. So there was a commitment from the central government people on using this data. This was a very exciting thing as far as I think this was this I must give credit to Professor Dhawan's complete vision, uh, because remote sensing cannot be a technology by itself. That ultimately it has to be useful, and not just useful. It has to be used by the stakeholders on the ground, even if not today, tomorrow. That was the spirit of those things. And apart from the two experimental satellites, Bhaskara 1 and Bhaskara 2, there was no other satellite still launched. There was no IRS satellite. This was all happened in 1980s, up to mid 80s or so. So, and then one very important thought came to all people. India is a federal country. Resources belong to states, not to the central government. If you know, for example, agriculture, forestry, forest belongs to the forest which is in Karnataka belongs to Karnataka. Forest which is in Madhya Pradesh belongs to Madhya Pradesh. So most all natural resources, except for the water, which is an inter-river, interstate issue, all resources belong to the states. So unless you get the states involved, there are so many states. Now, of course, there are 29 or 27 states and union territories involved in this process of establishing infrastructure for the utilization of data. This will not work. So there was another important thing that was given to us, and I was one of the person who was very much involved in this, that states should establish a small state remote sensing centers in which they will have people, their own resource people, and they must take up the utilization of this data for their states. So this concept of planning commission, standing committees, NNRMS, state remote sensing centers, and the ISRO centers. So this became a cluster of all organizations. In addition to, of course, there may be other small industries and other users, etc., where to take forward whenever we get the data from our own satellites, to take it forward for the end use. So this aspect of the actual evolution of remote sensing in the country, and all this, I must say, before any Indian remote sensing satellite worth its name was launched. And that was launched only in 1988, on March 17. And I must tell you, on this particular occasion, March 17 happened to be my birthday. And so in 1988, I was 40 on March 17. So everybody was so happy and I was so pleased that I am actually here for the remote sensing itself, because it coincides with my birthday. So this is the background to my work. But along with that, of course, I was very much involved in definition of the satellite. What kind of spectral band should be there? Should they be blue, green, red, infrared? But already you had some experience with Landsat data, but you wanted to make sure that you just don't copy Landsat MSS. But there were some issues with Landsat MSS. There was some oxygen absorption feature was there. There was some other problems with those things. So we avoided all those things and got into the definition of these sensors as well. And we also said that let there not be only a one camera, but let there be two cameras, basically defining two resolutions, 72 meter resolution as well as 36 meter resolution. So all this happened much before 1988. I hope this is the background which is enough.
Yeah, I mean, that provides an excellent foundation for our conversation further. You talked about how they were, just a 4 or 5 year history of, SAC when you joined. What was the environment like when you joined? What was the vibe? Because India did not have any launch vehicles. India did not have any satellites or anything like that. I guess you were using a lot of the Landsat data to do a lot of the work. So talk a little bit about, how was the environment during the time you joined and how it evolved?
See, one of the things is that SAC actually, although it is called Space Application Center, But it is basically a technology center. Uh, the environment, as I said, in SAC, there were major groups which were essentially developing microwave components, microwave sensors, which are micro radiometer, etc. There was this group which was in Earth stations for geosynchronous satellites. That was also providing training to a large number of people from other countries on Earth station reception and all that for communication satellites. There were electro-optical sensors development using optics detectors and all that kind of things. There was a data processing group which was extremely involved in what kind of corrections which you need to do for data. So it was basically a technology organization. But founder director always felt that this has to be driven by the people who actually use the data. That is where we, as the applications group, so I would say Space Application Center environment is the most ideal environment for anybody to interact with all these groups and get to know. That is why you get a much more rounded knowledge in the Space Application Center. If you go only to somebody who is only using the data, that will not do, because that kind of a work, then he will not be able to understand why a sensor person is saying so that this is possible, but that is not possible, etc. So the environment of the Space Application Center was one, technology plus all the so-called software plus the applications and stakeholders. Plus you also know that SAC had the heritage of a site experiment, that is satellite instructional television experiment, which was done by which was started by Vikram Sarabhai, but later on took up by Professor Chitnis and Professor Yashpal, which beamed educational material to many villages in 6 districts of India. And you had to do a lot of content development, do social research, what kind of programs are required by people in those tribal villages, etc. So there is a social context, and that is called the DECU, Development, Education and Communication Unit. So there is a full gamut of activities in SAC. So I would say, if anybody wants to get into any of these space technology related things, SAC is in that sense an ideal. And many times people used to compare that SAC is more like the JPL, Jet Propulsion Laboratory. So that was so environment was very good. But as I said, for me, initially, if you ask me from my background that I had in physics and the PhD that I had done, I could have gone into any of these groups. But it so happened that I got into an area which was more of a user or more of a analysis of data for applications. But I don't regret it, because I think that gave me a very different perspective altogether. So, and Dr. George Joseph and his team was working on the development of these cameras, LIS cameras at that time. And those LIS cameras were not like the Landsat multispectral scanners, because as you know, in multispectral scanner, MSS, or even the thematic mapper, there's an oscillating mirror, basically mechanical thing. And then you get, as the satellite moves, you get the images. Whereas by then, technology, we had these linear imaging sensors, charge coupled devices. So George Joseph at that time and Dr. Kasturangan thought that we should have these things, although that avoids the probability of failure of mechanical systems. That was one of the things. But it also has another advantage. You don't have to worry, because when in an oscillating mirror, when you go to the edges, the pixels become bigger than the nadir looking, whereas in LIS, all of them will be same. So in terms of processing also, it becomes easier. So these LIS cameras were built, and we were involved in seeing that the specifications, what should be the saturation radiance, because these are some technical things, but I must explain that major application for all our earlier remote sensing programs was agriculture. So if you want the cameras to work for agricultural applications, that means the radiance that they should saturate or the gain settings should also satisfy what is the albedo of crops or vegetation and not snow. If you design something for snow, then it is 100% or 95%. So what happens? The data with respect to crops gets confined to very small regions. So you are not able to discriminate within crops so much. So, these are the intricacies which we were involved to tell that this is, of course, this was all because we were using Landsat data, etc. But I must say one more thing here. Landsat, we were receiving at Hyderabad National Remote Sensing Agency then. It used to cost $2,000 for one CCT. And one CCT, computer compatible tape, covers 185 by 185 kilometers. If you wanted to do an exercise for India with such a large number of scenes which are required, that too multiple times during the year, you imagine the cost of the data itself. We used to have a problem even getting a few of them to do demonstration experiments, to get familiar with those things, etc. So I think it was worthwhile that we had to go for the Indian Remote Sensing Satellite Program, our own satellites, our own specifications, bands, etc. So that was most satisfying. So I think that was a situation at that time. One more thing I must tell at this point, because during that time, Professor U.R. Rao, by then Professor Satish Dhawan had retired, and Professor U.R. Rao was the chairman of the Indian Space Research Organization, and he was very keen that we must do national crop production forecasting. That essentially meant for the entire country, you must tell how much are we producing, how much wheat are we producing, how much paddy you are producing, etc. And we have not even launched the satellite that was being launched in 88. And I somehow was the leader of this particular team, which was supposed to get into these things. So he used to call, he would not worry about hierarchy. So he would just call to his chambers at Kaveri Bhavan in Bangalore. So he'd sit across his table. And I used to tell him, sir, in India, 60% of agriculture production comes from June to September, which is cloud covered. So optical data is not at all available. And in India, the field sizes are small, unlike in US. So this 80-meter resolution or 72-meter resolution will not allow me to do that. You require at least once in 5 days the data, not 22 days like IRS was being proposed, etc. So, this even now I remember my colleagues also, I tell them, Professor Rao would say, look, you don't tell me why it cannot be done. You tell me how it can be done. And as time progresses, we'll build everything that you are saying that we need to build. We need to build microwave sensors. Okay. We need to have satellites which give you data every 5 days. Okay. But don't tell me right now that you have all these problems. You start doing. You make a program. So this is something which I feel is a visionary approach which he adopted. So I would say that most of the things, particularly the name that India made in the remote sensing applications program, and the total program being a very model to many countries, is because of Professor Rao at that time. That was very, very inspiring to particularly our group at the Space Application Center. Yeah, please.
So you are, let's say, not an agriculturist and such, you are.
No, not at all. Not at all. Since you asked me that question, sometime in 1991, Professor U.R. Rao got a letter saying that they are looking for a person who could be the Director General of the Indian Council of Agricultural Research. And he telephoned me and said, Navalgund, I want to send you a nomination. I said, sir, I'm not an agriculture scientist. I'm a physicist, as thoroughbred as anybody from TIFR, which is the elite institution in the country. So he laughed. He said, I know you are a physicist, as good a physicist as he was. But I thought with your experience, you would be a better DG ICMR. But any IC, the Indian Council of Agriculture is ICAR. But anyway, he listened to me and he didn't disturb me further. But this is true. Yes. Yeah, please.
No, I asked that because there is two separate islands of knowledge that you have to bring together to drive end user application. You have to, let's say, know what is the realities of agriculture, like you beautifully talked about, the size of lands being small in India, the so many realities of Indian agriculture which are so unique to India against any other country in the world. And you also have to know what it means to connect it to space technology and satellite design and payload design for remote sensing and so on. So how is this culture being built up in ISRO at during your time, where you have to go learn about agriculture and how the end user behaves in India and how the capacity can be built up in the end user?
Yeah, in fact, we have had very close interactions with many agriculture universities as well as Indian Agriculture Research Institute at Pusa campus. First, in fact, we were doing ground experiments, actually growing, let's say, a crop like let's say wheat, and in, let's say, hundreds of plots in a farm. Each of them you give different amount of fertilizers, irrigate them differently, and measure what is their spectral response in those bands which we are likely to put on the satellites from the ground. And at what stage can you distinguish a crop from the other crop? That is one thing. Second is a crop which has more fertilizer compared to the other less fertilizer, or the one which has been irrigated, the one which has not been irrigated, that means it is having water stress. How do they differ in their spectral responses? And whether you can catch that is good enough to be caught by the sensor on the satellite. So this kind of experiment simulations actually on the ground, I was particularly engaged with all my colleagues. Of course, the team was multidisciplinary, as I said. There were some people from agriculture background, there were some from physics, some who were plant physiology, who knew what the yield would be. So on the basis of these things, we said that we must have very high radiometric resolution. That is at least 10 bits. In the initial stages, most of the satellites, even Landsat or our IRS 1A, 1B, used to have only 6 bits or 7 bits radiometric resolution. But later on, we got into 10 bits radiometric resolution. But just increasing the bits does not mean that you will get it. Consistent with radiometric resolutions, you must also have the sensitivity of the instruments to make small differences measurable. So you need to have better optics. You need to have many of the fast electronics because the data volume increases. Then we said this 22 days once a satellite comes, and again it comes after another 22 days. If that 22nd day is a cloud cover day, then you get once in 44 days. And if you have the crop total cover, the calendar is 120 days. So within 120 days, if you get only 2 data sets, it's very difficult to discriminate crops and find out what is the yield. So, just like your sampling frequencies in engineering, so we need to have every 5 days. So we kept on saying that every 5 days you must have an image. And I said you must have 10-bit radiometric resolution. You must have much better spatial resolution of the order of 20 meters or better. So these things basically forced, or I will not say force, but this was a kind of a feedback mechanism. Then the sensor people will say, we will design. Of course, we need to build better optics. We need to have better detectors. So that's how, IRS 1C came into being. So 1A, 1B did a lot of work, but that was not good enough. That was not enough. So we went into IRS 1C. So that is where, we got into shortwave infrared. That because the only data in the shortwave infrared can discriminate between one which is stressed because of water and the one which is not stressed because of water. That you could not do earlier in IRS 1A, 1B. So we said we must introduce shortwave infrared. We also said that we must have every 5 days. That's why they brought in wide field sensor. This is a trade-off. In all satellite designs, there is a trade-off. If you increase the swath, then you get higher repeativity. But if you increase the swath, you get higher repeativity, but your resolution, spatial resolution becomes coarse. So we had 188 meters. So I said, no, 188 meters we don't want. We want much better, about 50 meters. Then we also said that, you see, wide field sensor also should have shortwave infrareds. That they didn't have because that time detectors were not available for that kind of a thing. They were also expensive. So IRSC 1C was in that direction of meeting the actual user requirements. This is as far as agriculture is concerned. For example, urban applications, you can't do with 20 meters even. You need much better resolutions. So that is how this 5.8 meter resolution came about, the panchromatic camera, which was there on IRS 1C. But this also is because of Professor U.R. Rao. Professor U.R. Rao said, don't tell me about spot 10 meter resolution. We must be better than them. At that time, spot had 10 meter resolution, panchromatic, and 20 meter multispectral. That was one of the considered the best at that in 90s, etc. So Professor Rao said, no, we must be better than that. That is how this group developed the 5.8 meter panchromatic camera. And that became an extremely important camera. At that time, in 1995, when it was launched, that was the highest civilian resolution, civilian spatial resolution satellite. So that was extremely good. So these, the definition of the specifications broadly, not everything they could do. I also, I was always, we were never happy in the sense that they gave us something, but we said, no, this is not good enough. So that is how that wide field sensor, which was a two band means only red and near infrared, and 188 meter resolution and 5-day repeativity. I said that will not do. That is how Dr. George Joseph said, no, we will get into this one. So that is how advanced wide field sensor was built. And this advanced wide field sensor was 56 meter resolution and 5-day repeativity and 10-bit radiometric resolution and 4 spectral bands, not 2. And that was launched. Of course, it takes time. And that was launched only in 2003. But, coincidentally, by that time, United States Landsat program had failure. I think Landsat 6, I'm not very sure. I think Landsat 6 was a failure, and they did not have any satellite at that moment because US, one of the major experiments they do is what is called as foreign crop condition assessment. US monitors the crops, agricultural crops of the entire globe regularly. And this was not possible. So they set up an Earth station to receive IRS P6. That was the one launched in 2003. They started receiving the data, AWIPS data, and they did most of the foreign crop condition assessment and many of their programs with this AWIPS data. So that became an extremely good sensor for global crop condition assessment. And what happens when you get every 5 days, and you imagine 120 days, every 5 days you get it. So you get a very large number, 24 of them, 24 points you get. And this is something like a distribution curve, because the plant grows. So you get an increase in the ratio, NDVI, near infrared to red or any of those devices. And then it starts decreasing. But, for us being we are also analytical, we are physicists. When when the curve increases and when the curve starts on the other side after, let's say, 60 days, etc., if it goes very fast, steeply, that means the yield is likely to be less. That means it is maturing very fast. But if it matures slowly, the grain yield becomes more. So when you get a growth profile complete, then you get many parameters. One is the entire area under the curve, maximum peak, full width at half maximum, the slope while it is decreasing. All such things are useful in finally making a model for yield using remotely sensed data. So all these things, come from the combination of people who have physics, analytical background, and agriculture who understand. So all these things were developed by basically our group at the Space Application Center. And eventually, I must tell you one more interesting thing. From 1985-86, when Professor Rao started meeting Secretary of Agriculture, till 2012, when I retired, I must have met at least 22, 23 secretaries of agriculture to Government of India and made presentations to tell them that, look, this is a very useful thing for the country to know what is the production that is likely to be there, because that will help you to make decisions on whether to import, export, how many wagons are required, what should be the minimum support price. I mean, a number of policy decisions, etc. So you please set up your own institute. We are an R&D organization. We cannot keep on doing it for the country. Our job is to develop tools and techniques. So I tell you every time, including Mr. Sharad Pawar, when he was the agriculture minister, I have made the presentation. We were never tired. I mean, we kept on doing it. And I must be very happy to tell you that in 2012, when I retired, by then, at that time, the very important institution, that the Mahalanobis National Crop Forecasting Center, was established by the Ministry of Agriculture at their Pusa campus, IRI, New Delhi. And then, of course, they said, okay, we will do this. We will start doing ourselves. But you send your person on deputation to be the director here. So I nominated a young man who is doing extremely well. And more recently now, when there is this Fasal Bima Yojana, the Prime Minister's very pet project, when you have to give money to the farmers depending upon how much crop loss is there, insurance, etc. This satellite data is extremely useful. I'm amazed at the kind of work that he's doing, which I never thought at that moment. I will give you some examples. Some farmers, or I don't want to name any persons. Some farmers, let's say, put 100 hectares, they say, while putting insurance, that he is going to grow a crop A. But actually what he does is only on 50 hectares, he might sow. And later on, once the season is over, harvesting is over, etc., then the total production obviously is less. Though then he will say, you give me for the entire thing. So you look at the images of the previous season and see, look, you didn't even sow. How are you eligible to get that much money? Or, for example, you are supposed to grow crop A, but he has grown crop B. That is also a violation. Of course, most of the people would think that if crop is supposed to give 100% yield, or some, let's say, 2 tons per hectare, and it has given you only 1 ton because of drought, etc., then he has to be compensated. Or if it is 75%. So all such issues which are there today are being actually looked at, examined by this center, is Mahalanobis National Crop Focus Center. Of course, the word Mahalanobis is because Mahalanobis was a great statistician, scientist of India who introduced crop statistics in this country in, I think, many years ago when Britishers were there, even at that time. So that is how it is in his name. So I'm extremely happy because what we started in, I joined in 77, but more or less the work started from almost scratch from those years to today. I think it has taken a full circle in ensuring that remotely sensed data from our satellites is used for an extremely important purpose on the ground, which is useful for society. And like this, there are many. There is for glaciers, it is there. For forest enumeration, it is there. For coastal zone is there. For fisheries, for example, I must tell you about fisheries. fisheries work also started way back in 1980s, early 80s. At that time, only sea surface temperature, which we were not measuring, but it was available from NOAA satellites, the US satellites. You could distinguish the temperature, sea surface temperatures between two regions, and the fish had a probability of aggregating at a particular specific temperature ridge or something like that. So it started from that. Later on, we had a satellite for ocean color. That was in 1999. Ocean color actually measures the ocean color. But the ocean color measurement actually means the phytoplanktons, the unicellular plants. Now, these actually are like plants. They absorb blue and red radiation. They reflect green and infrared radiation. But this is so small from the sea surface. It's only 3 to 4%, 4 to 5%. By the time it reaches the sensor, 100%, 95% comes from the atmosphere. So you require first very sensitive instruments. Second, you require an ability to subtract the contribution from the atmosphere. Then you say so much phytoplanktons or so much chlorophyll content is there in the oceanic waters. Then you know that that is a food for herbivorous fish. And herbivorous fish are again food for carnivorous fish, etc. So by identifying these phytoplanktons from the satellite data, by measuring the sea surface temperatures, by also looking at winds and currents, you are able to make that these are the areas where fishery is likely to be more probability than other places. This has been an extremely popular application with the fishermen. And we used to send this, translate it into a vernacular language, and fax that information within 3-4 hours of the receipt of the satellite data to their fishing harbors. They will look at it and go. So they will basically save diesel because they don't have to keep looking for places. Second, they used to get higher catch. So this fisheries is another very important application, which is by India. And this has been acclaimed. And this is then we have slightly better ocean color instrument later on. We had in 2000, late 2009 or 11 or so. And of course, there is another argument also. Fishermen will say that you give us these forecasts all 12 months. And obviously we said, no, it is not possible because during the cloudy seasons, since optical data is not available, it is not possible to give you. But it also coincides with the breeding, fish breeding. And if you get those charts during that time, juvenile fish will get killed and the sustainability gets a problem. So in a sense, it was a very useful thing for us to make sure that it is available only during the other times, etc. And if I'm not mistaken, Indian Institute of Applied Economic Research in New Delhi has come up, they have done cost-benefit aspects of this, particularly for fisheries. They have come up with a number like 50,000 crores benefit to the country because of this single application of fisheries. You can, after all, how much a satellite costs, including its launch, maybe about 1,000 crores. If you talk about 200 to 300 crores of a satellite and maybe another, I don't know now, 300-400 crores of a launch, plus ground station receiving and all that. So, it's a very, very beneficial application. So I think the major point that I want to say is the feedback from the applications, the actual usefulness, how do they translate in terms of actual specification, in terms of parameters, gets back into the, the people who develop these sensors, put them in the satellites, has been the main force or thrust. And I have been very much excited for these things of my for my contributions in ISRO. I mean, I just said about, of course, these fisheries and these things, but I had equally role in related to atmosphere, clouds, and even IMD was skeptical initially about satellite products. But today, if you see, particularly in case of cyclones, in 1999, when the super cyclone hit Orissa coast, I don't remember, but I think 40,000 people or so died. But uh, over the years, the cyclone track prediction and landfall point have improved considerably because of the inputs coming from satellites, which tell you where the genesis of the cyclone is, what is the direction in it which is likely to move. That is, of course, again, a modeling efforts are there. What are the wind speeds which it will have? So within plus or minus 30, 40 kilometers when you come, and also 24 hours, 48 hours, much before it is going to have a landfall point, you are giving this track. And that itself today, even a bigger cyclone has hit in 2013 and very recently, the number of casualties is very less. So the remote sensing satellites, whether in ocean, land, or atmosphere, all three, to which we made contributions, have helped tremendously. In fact, we also built a scatterometer. A scatterometer, measures basically when you send a pulse to the ocean surface and you get back the scattered signal from the ocean surface. If the ocean surface is absolutely plain, high school physics, Snell's law, you get zero signal back from that to the satellite. But if there are ripples, if there are capillary waves on the sea surface, then you get a scattered signal. And that scattered signal, if you measure and inverse it, you get the wind speed. Okay, because capillary waves or all these things are produced by the wind over the oceans. So thereby you are able to measure sea surface winds. So from this scatterometer wind surface measurements globally. And there was a time in about 10, 12 years back when one of the scatterometers which was developed by NASA failed, QuickSat. It was only the Indian scatterometer, which we called OSCAT, was the one which was providing wind vectors over the entire globe oceans. Now we have three scatterometers. So they are giving. Another very important thing was the one point which I want to tell you about applications, which I initially said is related to this use of microwaves. I always said that Indian agriculture is 60% comes from Kharif season. So we need a synthetic aperture radar. But, the technology was probably was not adequate at earlier times. But we never said, we never, we never said that we will not use data from other satellites. So right from mid-80s, there were a shuttle radars. There were some radars which were flown on shuttles, so which we used those things. We were familiar with those things. Later on, ESA, European Space Agency, flew a satellite in which there was a synthetic aperture radar. Then there was a Canadian RadarSat 1 and 2. So we as the end users or the application scientists, we were familiar with how to use microwave data. So we kept on telling that, look, don't worry about when you build a microwave synthetic aperture radar, that who will be using it. We are all very familiar with it. And we had already trained all our users in state remote sensing centers and many of the users, etc. So finally, when India launched its own synthetic aperture radar satellite, RISat, in 2012, that data could be immediately used by all the people who were supposed to have been using these things, etc. So I have never hesitated in equipping ourselves or my colleagues in using the data from whatever sources it is available, so that you are prepared. When we have our own satellites of that kind, you are able to use them without much time lag in those things. You are familiar already. So this is something which also I think it's an important lesson. Sometimes because of constraints, non-availability of technology, non-availability of components, uh, and also because of embargoes that you are not able to match sometimes the kind of sophisticated instruments or measurements which are required for the country. But that should not deter us from not using or not being prepared if and when the data becomes available. So I personally feel that that has stood in good stead for most of us. I mean, I hope I conveyed what I wanted to convey to you.
Yeah, absolutely. And one of the interesting aspects that you didn't touch upon, which might be interesting to talk about, is this embargo and the level of hardware that you actually need to realize many complicated cameras. And ISRO, I think, does a very good job of, let's say, designing cameras or integrating them. But you need to depend on a lot of the semiconductor industry. You need to depend on a lot of the sensor industry, which comes together to make these cameras possible, right? So you have to then look at, and many of these industries are not in India. You don't have a very good camera sensor production company in India. You have to depend on many other export suppliers from abroad for getting all of these kinds of critical equipment to realize some of these cameras. So what has been your experience, let's say, from the end of 70s to until now, with respect to some of these constraints and how they were overcome?
See, I must admit, although my background is physics and I have had some knowledge of hardware related aspects, but I did not actually work on any of the hardware like some of my colleagues, as I mentioned, Dr. George Joseph or Kiran Kumar and those people. But obviously, as far as electro-optical sensors are concerned, there are three important things. One is the optics of high size, higher aperture, large aperture optics with the kind of surface accuracies that you require when you want to go into very high spatial resolutions, etc. 5.8 meter is okay, but from 5.8 meter, you want to go to 1 meter or even a fraction of a meter, then you require much higher aperture optics with the kind of surface accuracies that you require. That is one thing. Second is you require detectors which are very sensitive. That time TDIs, time delay integrated devices, etc. And then you also require fast electronics because the data volume becomes large. Then you require data transmission, etc. So there were, of course, issues related to all these things. For example, we probably my other colleagues would know better. We did not have access to either the TDI devices earlier, nor did we have all the components that were required this one. And although there were efforts made in the country to build optics, there has been a very extremely large infrastructure built at Bangalore in our central EOS, where we are now, I think, making even 1 meter kind of aperture with the kind of surface accuracy that is required. Otherwise, we could not have done Cartosat 3, which is 30 centimeter resolution. But during the late 90s and beginning of 2000, yes, we did have some of the difficulties that you just mentioned. But some ingenuity was used in overcoming these things. You may recall that you recall, or I mentioned to you that 5.8 meter panchromatic camera. But the same camera system was used to get 1 meter resolution in 2001 in a satellite called the TES, Technology Experimental Satellite. It was an experimental satellite, but this was done using a technique called step and stare. What it actually meant was, I was not involved in this, but what it meant was that as the spacecraft is moving, as that camera or the optics take one step and stare at the same point for this one, so that you integrate that signals, and resolution becomes better in that. That is how 5.8 meter was brought to 1 meter resolution. Of course, there are possibilities that there might be some degradation of some MTF, or some of the things is possible, but the spirit was to get it. So some of these techniques have been employed in order to overcome some of the difficulties which we had earlier. That is how the so-called high resolution after 5.8 meter, a host of high resolution satellites from Iconos 1999 or 98, I don't recollect, digital camera. I mean, many of them have come up after that. But by the time we got into high resolution was probably in 2005. We had a Cartosat 1, which was a stereoscopic 2.5 meter resolution. Then I think at that time 70 centimeter aperture optics was built. And later on, Cartosat 2 was done, which is a 1 meter resolution. Of course, these are panchromatic. Later on, of course, multispectral was also added to that thing. So yes, there were periods in which there were difficulties. During that time, of course, one has taken recourse to doing some ingenuity in designs. But I think after that now, in the last maybe a few years, some of all these devices, etc., are become available. And our own institution at Semiconductor Laboratory at Chandigarh, Mohali, they are also making CCDs and other things, etc. But overall, in the area of these detectors and devices, maybe I think not me alone, but India could have taken a much better efforts right from the beginning. Yes, I agree with that. We could have done much better if we had probably put more emphasis on those things. That is true. For example, even microwave SAR, it required devices, this receiver and transmitter modules to make. We had to get the gallium arsenide devices qualified, etc. So I personally myself had gone to what is that institution called GATEC in Hyderabad. So people, only when there is enough demand and importance given, the other institutions also rise up to that challenges. Otherwise they will also be doing some research. So it's a mix of both things. You also have to make demands on institutions. Institutions will, to challenges. Then they will say, I need this, I need that. Then of course the government has to be convinced, and you get funding. So the process, I think, is still on. I mean, now you have so many other things coming up. So, but detectors is also another thing as very important. Yes, I agree with you. Yeah.
Right. And one of the challenges here is how do you convince end users to trust what you deliver? And because, at the end of the day, end user communities in agriculture, fisheries, whatever it is, XYZ, there is let's say they know the problem and they see the reality of that problem on a daily basis. But when you, as somebody who's coming with technology to solve that problem, there can be, mistrust, or they may be also that they see you as an outsider to that community, and, you're coming up with maybe unreasonable aspects that they may think of, that this is not maybe for us because it may not work in scale, or it may not be useful on a daily basis, or whatever it is. There may be such, let's say, kind of a hindsight to their judgment of what you're trying to provide. Have you seen such experiences in trying to go build capacity in end user institutions in India, and how maybe have you overcome such problems?
No, this is an extremely important point that you have raised, and that is why I took some time to explain to you Professor Satish Dhawan's concept of this National Natural Resources Management involving the central agencies, involving states, final users in right from the beginning. In order to make sure that the technology that you develop or the solutions that you provide are ultimately going to be used, absorbed by the final end stakeholders. I have 3, 4 points. One is the problems should be genuine problems of the country. Knowing crop production is a genuine issue of the country or even of those people. Farmers have their own issues related to agrometeorological advisories, whether it will rain, whether it will have humidity, etc. Fisheries, where do I get fisheries, etc. So first is the problems themselves which you want to address. They should be genuine problems of the country, issues. So this is one thing which we did in the early 80s itself to identify, sitting with all stakeholders, right from the ministries, states, and the non-governmental organizations, the people, NGOs, with all of them. This is first thing. Second thing, very important thing is you involve these stakeholders in the definition of demonstration experiments also. Don't just say that, yes, okay, I will develop a big brother attitude and you give it. No, you involve them right from the beginning of the formulation stage. That is the second thing. Third is all of them may not understand, but at least a few of them, you tell them that you need to know how these things work. That means a certain amount of training or capacity. Finally, the actual demonstration of those things in there along with them. Then only and all this we have adopted in almost all of these things that I mentioned to you. So this end users basically believing that this is useful to them is important only when you go through all these steps. Now, there have been always skeptics. For example, I will give you in mid-80s, etc., Forest Survey of India. I mean, again, when I'm taking the names, you please don't consider it as I'm saying any aspersions on that thing. See, the government of India, there was a problem that the Forest Survey of India said that they have, I think, 21% under forest of the geographical area of the country. And National Remote Sensing Agency, with their Landsat data analysis, they came up and said that they have, we have actually only 16% or so. So this became an issue and this had to be resolved. So there were joint teams made of scientists from here as well as scientists from forest, I mean, those people who are working in forest, etc. So it turns out at that time that the actual forest area came to 19%. How did it come about? Because many of our people while interpreting felt that during the winter when there is no cover, when the leaves are shed, etc., it gives a different kind of signature. So they treat it as there is no forest. So that is how proper season you have to use the data. So you need subject experts in these things, etc. So finally it came 19%. So that was a reconciliation done at that time. So now, then the parliament said that every 2 years, the Forest Survey of India has to put up a report in the parliament, what is our forest area? There are no other questions, okay? So they have to do it. So and they have to identify which are the areas which are encroached, which are the areas which are degraded, where afforestation has actually taken place in a map form. So this is a job given to the Forest Survey, not to ISRO. It is to the Forest Department. They have to do that. So obviously now they initially were very comfortable with using Landsat data. Now, of course, as long as Indian data was not available, it was fine. But after 1988, once the Indian remote sensing satellite started becoming available, so, it is always very difficult to change people from their comfort zones. So they were not willing initially to change from whatever they were doing with using Landsat data to that. So you have to show that you get very equally important, equally reliable results from this data. So it had happened. It had happened in this case. So a lot of efforts was put in. So after some time, yes, economics also plays a role in making these decisions. So today, the entire department uses the data to make the forest related things, etc. Now, agriculture. In agriculture, what happens is uh, they will always say that there are two parts in agriculture, in any crops. One is the area. So many hectares, this crop is grown. Second is the yield. Yield is a very variable part of it. So you can give area very accurately from your satellite data, but yield you can't give. This is a general criticism, etc., etc. Then, when we had joint teams, I used to ask them, when you say that 280 tons or 250 tons, 2 million tons is grown in this country, on what basis do you give this? Do you weigh each grain in this country? There is no answer to that, right? That is based upon what? That is based upon a few hundred crop cutting experiments which are done after harvest, and then using some statistics, it is aggregated to taluka, states, districts, and to the entire country. Now, how do you choose those sites? God alone knows, because earlier times, it is starting from right from beginning of the British times, where the actual should be done. Now, scientifically, you should choose sites so that all the dynamic range of the yield variation is encompassed in the choice of these crop cutting sites. And if you do all these things, then only you can do this kind of a statistical aggregation. So can remote sensing data help you in identifying sites on the basis of the vigor that you see on the satellite images, which we did together? So they were convinced that, look, now I need to change, or how many I should do. It depends upon these things. What is the way? If it is a complete homogeneous area, then you don't need too many sites. But if it is the heterogeneity is large, then you require more. So all these things are done, when you do together. That's what I keep telling, that when you do these things together with confidence of each other, that you are not having any superiority complex or big brotherly attitude and do these things, etc. This is how it has grown. And so there have been instances where people, in the initial stages, people used to say this is at best useful for planning level, not for actual thing. Now, I must give you an example of groundwater, drinking water. See, groundwater is below the ground. Satellite remote sensing doesn't see where water, it only sees surface water. But satellite sees a certain what we call as surface expressions or signatures, which show you the convergence, with whose convergence will tell you which are the most probable areas where groundwater is likely to be found below the ground. So this is what is done using satellite data for all 10 or 12 states of this country. Now, on the basis of these maps, which show what are the prospect zones, and villages are also marked on that. And those villages which have no drinking water source, then we say, you please go here and do the digging or the bore well. And even just year before last, I think 2 years back in Karnataka, there was this problem. And they said, look, there's a drinking water problem. So they have their own department, geology department and drinking water. So they took up the maps which they themselves have prepared and found out them. They updated them using the recent satellite data. They went and got the drinking water. I mean, basically success of the bore wells, and provided the drinking water. So when they start seeing the success of these maps, the information that is there to the extent that they require, then only this. And this is the process. So there are many experiments. For example, even, urban areas violations. Today, people are using, earlier in 5.8 meter in 1995, in spite of the fact that I keep claiming that that was the best civilian satellite of highest spatial resolution at that time, no urban planning person was convinced that that data can be used. They only used it for perspective planning, what they call as, perspective planning. For example, Bangalore Metropolitan Regional Development Authority, complete play area. If you want to do some planning, you can use it. But if you want to do town planning, that means where they start showing each layouts, etc., it is not useful. But today, when you have much higher resolution satellite data, obviously 1 meter and so on and so forth, yes, they can be used. But I keep telling them now that, look, today, you don't have to use satellite technology. I mean, of course, I'm not in the business of, I'm not there in an active service. But when somebody asked me recently, some people are asking for better than 50 centimeter satellite for some of the applications, etc. I said, please don't do it, because whatever you want, much better, 10 centimeter, 20 or 30 centimeter resolution satellite data, you can do it for inaccessible regions, across the borders, for surveillance purposes, etc. But within the country, when you want to require it, of that kind of a resolution satellite data, you are basically requiring it for infrastructure development activities. And those are essentially confined to a particular region. And today there are drones which contain a large number of sensors which are inertially referenced. You get very high resolution satellite data with proper mapping, etc. Use it. You can also do stereos. So today the technology is advancing. So you don't have to use satellites for everything. Okay, satellites are useful for many applications. I mean, of course, ocean and atmosphere, you cannot cover with the drones and such things, but that essentially a large number of parameters which are required, they have to be done by satellites. In monitoring environment and all these applications which I said, yes, you require satellites, but satellites are not necessary for applications in your own areas for more of a infrastructure development thing of a very specific areas, let's say a few tens of kilometers, square kilometer area, etc. Why should you only build a satellite for that thing? Unless you say that I want a satellite of high spatial resolution to map each and every inch of this country. But then also you will have problems because you have forests, you have so many other things, they keep changing. So you have to make a judicious choice of the kind of data that you require. And I have found that it is basically confidence building with the users. You should not bluff. I mean, if you ask me in a colloquially, you should show them, involve them right from the beginning, do experiments jointly, show them and demonstrate that thing, utility, etc. And that is what has been done in the, I would say, all our earlier chairman, Professor Dhawan, Professor U.R. Rao, Dr. Kastura. I mean, that is how this whole thing has been built over the years. So I hope I have made my point.
Yeah, absolutely. And one of the interesting aspects is this emergence of, let's say, the geospatial hubs of many companies in India, especially in and around the Hyderabad belt. And, a lot of them, of course, are now doing business globally. And, they are also doing a lot of work across the international geospatial arena. So can you, describe how these people were empowered?
I tell you, I have some very personal experience of this kind. See, I was also at the National Remote Sensing Agency, Hyderabad, during the period 2001 to 2005. From SAC, I was sent there. During the years of late 90s and beginning, there was this concept that why should ISRO be doing all the work, etc. So a large number of industries should take up this. So a lot of geospatial industries, vendors, so-called that time, they came up. In fact, there were 200 of them in Hyderabad and surrounding areas, and some in Bangalore, etc., etc. But during that time, one of the problems was they were dependent. They were dependent on projects and other things which was to be given by the government or government-sponsored schemes. So they were in some sense handicapped because obviously the catchment which was available was limited, and if you have too many people looking for the same slice of cake, there were difficulties. So geospatial industries at that time, and also the kind of advances which in satellites which have come now more recently after the high resolution satellites of 1 meter and better, and also a lot of software related things, etc., which was not there during those times. That time, I did find, although there was a lot of encouragement to have these geospatial industries during that period, they did not blossom as much as possible, as because they were also not looking out so much, generating work for themselves from outside, etc. Although there were some few who were taking up work in Nepal and some African countries, etc. But now, and also I must tell you about the software which is required. You see, if you, at that time, it was mostly the ArcInfo GIS software or commercially off the shelves, some of these software, etc., which are by no means inexpensive. So the overall, what shall I say, environment was perhaps not so conducive for this growth. But in the last 10 years or so, I think in terms of advances in the satellite resolutions data, in terms of open source software, in terms of the decrease in the cost of these computer analysis systems and all those things, etc., and the business which is outside, and a large number of young people who can adapt to these things. Plus, there is a convergence of this GPS, and also in those things. So all this put together, I think the situation is extremely encouraging, in my opinion, for doing a large amount of geospatial work in the country. And it is not just services and products. Ultimately, as far as the user is concerned, he is interested in a product, which is useful to him, or provide a service to him. So now I think I see a great potential for Indian geospatial industries because of this. And tomorrow, hopefully, they should also adapt and see NAVIC. I mean, our own regional remote sensing. I mean, our satellites for navigation, GNSS or NAVIC, what we call navigation satellite system, which also provide you coordinates, XYZ coordinates. So put together that there is a lot of location-based services which are to be come up in the country, which are already there. Although GPS has become embedded in many of the things, but it is possible that if you get into using Indian navigation satellite data plus the remote sensing satellite data plus the GIS, a lot of other attribute data, make location-based services, make products which are directly usable by somebody, I think there is a lot of scope for that thing. I'm quite convinced that although at that time, when I said beginning of 2000, there were difficulties, there was not much growth of the market, but now I'm sure there will be a growth of the market. Plus also, a large number of constellation of satellites. Some people can get into building up constellation of satellites, which are, earlier this miniaturization and smaller satellites, etc., was not heard of. But now technology was so much advanced that if Planet Labs can give you everyday data, I mean, why not? There are many applications like disaster monitoring or many of the things which require data of high coverages, I mean, very frequent coverages. So people could do. There is a greater demand for, till today, constellation of satellites, both carrying both the synthetic aperture radar and optical, because many a times disasters which are floods or cyclones or any of those things are always covered by clouds regions. So you require SAR, but SAR also, which is lightweight, I mean, not a very big SAR, and constellations, so that you get the data when you want it. That is one of the problems, So a constellation of that kind of a things is very much required for disaster monitoring throughout the world. Recently, somebody has launched, I don't know whether it is some country, synthetic aperture radar, 1 or 2 satellites small, weighing less than 400 kg or so. But this is an area which is required. But of course, many a times people keep saying that the disaster related things are all public good. Will you recover the cost that you put in? So you will have to find ways of turning out this data fusion and data integration into products which a particular user can directly use, and that has a value. So, if I remember correctly, somewhere I read Landsat 8, when they made the Landsat 8 data freely available to the global community, just simple argument, they said that when there is a lot of business in value addition, data by itself should not cost. You give the data free, there are a large number of people who will use this data, add value to that one, and they will start making products, and that will earn them profits. So overall industry, overall country makes, does get a return for the money that you have spent on building the satellite. So that's the concept which is gained momentum. Okay.
Right. And one of the aspects now you talked about is the emergence of these small satellites. And you see now, many companies, also now some startups in India like Pixel, targeting to build these constellation of small satellites. There's a physics limitation, of course, as to how much limits you can get with these smaller satellites due to pure physics driving a lot of this image resolutions. But you see a world where ISRO can work on newer technology like higher quality thermal imaging, or higher quality SAR satellites, and these companies that are emerging for the first time in India can take over some of the lower end imaging needs, 3, 4, 5 meter kind of data, where they cannot, let's say, build 30 centimeter data in optical, or 50 centimeter SAR or something like that, where the investment is too large. So do you see that possibility emerging in India in the next coming years?
Yeah, definitely. I see that thing, and I entirely agree with you. I think any government-based space research organization should concentrate or should focus more attention on some things which are advanced technology, which require a certain amount of infrastructure related developments. You mentioned one which is extremely important, that is the thermal infrared region. Thermal infrared region with better spatial resolution is an area which we should concentrate. And those things which are like making electro-optical sensors visible and near infrared with moderate resolution or even better resolution of 5 meters or some such thing. I think those are things which you have already demonstrated very well. They can be taken up, and whatever infrastructure facilities are required for testing them and ensuring quality, calibrations, etc., they can be provided by the ISRO, which already has many of these things. And I think these are the things which currently, whatever that NewSpace India Limited is engaged in, I'm sure they will be doing those things. And one should concentrate more on advanced technologies. Synthetic aperture radar is something which, in all microwave sensors for that matter, is something which I'm extremely keen. For example, we only talked about SAR and scatterometer, but there is also another one which is altimeter. Altimeter is also a very precision instrument which measures the sea surface height, which is also important in many tsunami related things. We haven't developed, and that requires very, very precise orbit determination. So those are things which we should, we meaning, I'm no more a part of that, but I think the bigger organization should concentrate on. There is also, one of the things that we are, ISRO and JPL, NASA are building, that is the dual frequency, S and L frequency radar, that is called NISAR, NASA Indian ISRO radar frequency, which is a 12-meter unfurlable antenna. So that is something which is a global mission which will measure surface deformations through interferometry globally. It will measure the biosphere globally every month, and it will also look at the cryosphere So these are more of science related things at a broad level. So that also is both technology wise as well as data wise, processing wise, and science wise, extremely important. And I'm sure, I think there will be a lot of emphasis on that kind of work also. Broadly, today, uh, when I see after 40 years, remote sensing is a tool, right? And one, it can be used for large studies in global change, climate change studies, etc., which requires, let's say, 40 years, 50 years, calibrated data from different sensors, different satellites. If you say sea surface height, what was it 50 years of 40 years ago and today, in terms of a fraction of millimeters? I mean, today you measure with one satellite, tomorrow you measure with another satellite, or sea surface temperatures, or any of those related things, which are extremely difficult unless you do a large amount of consistent measurements, standards, calibrations, all these kind of things. So that is a kind of science, even including greenhouse gases, like you measure carbon dioxide or methane or any. So that is one kind of work which remote sensing satellites have to do, and those are different kind of measurements which are. Second are these operational remote sensing satellites, which are used for applications, day-to-day applications, etc., which need not be done by space agencies. I mean, they can be done by many of the things which are there. Third, of course, there are derived from this knowledge, people are also doing planetary missions. I mean, after all, it is the same set of sensors. That's why I took a lot of interest when Chandrayaan-1 was launched by India, because I said, look, we are the people who have already dealt with remotely sensed data. And after all, it is, instead of the Earth, this is a data which is looking at the moon. And in fact, there are advantages, because moon, there is no atmosphere. On the Earth, the atmosphere corrupts my signal. So you need corrections, whereas the signal on the moon without atmosphere. So it is much better to do that thing. And moon, the gravity is less, so you can go to lower altitudes. You get much better resolution. So doing remote sensing of the planets has its own advantages. Of course, not everywhere. Venus has a problem, but Mars also has a less atmosphere. It is only half of what Earth size is, etc. So remote sensing has different, what shall I say, objectives. One is science, other is operational applications. And the third, point is these no more data. Data has to be converted into products and services, which is very important. That only people who understand the users have to do that. So they have to interact very closely with the users and do that kind of work. So that is also another thing. Third, of course, is this, the what they call as constellations and trains. The concept of arrays, formation. There are many such things which are also there. That is, of course, again, a different kind of remote sensing, where you need to have communication between different elements, different satellites themselves. And when you get the data, there is a lot of development of software in order to make sure that the data becomes useful. So that is a different third type of. So there are different dimensions compared to when we started. We were only more or less worried about how do I get this data, how do I use to identify or map something, etc. But today I think it has gone beyond those things. And the other part, which is absolutely related to pattern recognition, surveillance, that is an entirely different set of remote sensing, which I don't have much familiarity. So there are different aspects of remote sensing.
Right, and actually that brings me to this question of artificial intelligence and machine learning coming into remote sensing today. You have broadly three main spheres combining all of these. One is, people who are trying to implement intelligence on board satellites. For example, I work with many companies here in Europe, for example, who are trying to implement, very high quality GPUs, very high quality computing on board satellites, where you can make satellites more aware and intelligent. For example, how do you make sure that you don't image cloudy areas, and you only image areas which are visible and usable data for that matter, and to increase the amount of data that you can use on the ground, instead of downlinking data, for example, that has clouds in them and you have to post process them, or it may not be completely unusable at all, for example, right? So you're adding intelligence to satellites by themselves, one layer of it. Second is, you're trying to integrate cloud so that the delivery of the data becomes seamless and very high speed with respect to cloud. And then you're using, as you said, for example, pattern matching or machine learning or object identification, and all of this to post process data to deliver real insights on top of it, which can go into any banking system, or it can go into many other systems that people can use directly, or so on. How well prepared are we in India for this, or do we need, let's say, a dedicated group that looks at all of this to fuse not just satellite but also ground-based data, statistics, drone data, air-based data, anything like that, so that the quality of the data set becomes extremely big and complements each other to actually give more usable insights and usable services to end users?
Yeah, I entirely agree with you. In fact, today I have seen many uh, institutes, particularly IITs. There are professors who have been working on such things, perhaps in their own domain and in a smaller groups on artificial intelligence, machine learning, pattern recognition. I remember having met a person, Rotel or somebody in IIT Kharagpur, IIT Bombay also. So there, in many academic institutes, there are people who are working on this data fusion, machine learning, as well as artificial intelligence, in order to use, or even cloud computing. In many of these aspects, they are all working using remotely sensed data, data mining related, etc. So that kind of effort exists in India. Now, whether all of that will relate to a focused effort in making certain final products and services which the industries or somebody else can take it up, that I do not know. Honestly, I do not know, because I'm not familiar with those things, to what extent they have graduated, or are they willing to spend their efforts, because these things will require some efforts of some intellectual level in which they will have to invest beforehand, and then go in for the actual commercialization of that thing. So this kind of environment, whether it has come up to, I'm not familiar. I'm sure it must be there. But as far as you said, artificial intelligence, many years ago, we had this problem, exactly what you are telling me. If it is a cloud, then we need not image the data, because it is unnecessarily adds to data transmission. Earth station, Earth station has to receive it, and then you find the data. Obviously, you need to develop some algorithms which detect a pixel which is cloud, which is not cloud, or even if you have to detect it, you see it much before. That means there has to be some advanced information so that you switch off or whatever it is. Also, I remember there used to be some problems associated with the distinction between a cloud and a snow also. Because both of them are highly reflecting from the top above when you see them. Then we were also worrying about which the spectral band, the cloud and the snow will look different, so that you use this so-called discriminatory, this one at that particular band. But all those things were very primitive and experimental in nature. But I think today data mining is something which people should because there is so much of data from so many satellites of same areas taken for different intervals of time with different conditions, etc. All that can be used in order to make some intelligent conclusions or observations, which people are doing in what shall I say, in probably defense areas, etc. I'm sure they are doing those things, And constantly they are doing because they need to update themselves. But in the civilian domain, such things to be useful, as I keep mentioning, it has to come in the form of a product or a service. So that is something which currently, to the best of my knowledge, it is more on the research areas, etc. Private industries, if they need to do, they must invest in certain intellectual efforts. But that is the way it will go, definitely.
Right. And from a, let's say, purely kind of non-technical aspect of all of this, one of the things that I definitely wonder is, a lot of the countries, even around the world, they kind of fail to communicate to its public as to why they should spend on space, especially developing countries. And for me, there's again a model that India can pioneer there by involving certain economists and social scientists to come up with yearly framework that can be updated to kind of tell people what is the value in productivity in certain communities and the impact on the GDP that it has for certain applications that are rolled out across the country, right? There is some limited evidence in that sense, where you have certain research papers that tell certain case studies at certain instances of time, but these are not rolling frameworks, and these are not taking into account the entire geography or the entire size of the community in India, or combining the entire effect of remote sensing products in that case. So my question is, how do you make sure that we involve certain experts who are either economists or social scientists, or to work with space scientists to map all of this, so that the average Indian actually gets to know what is the impact that ISRO is having, or the remote sensing data community is having across, and then there's more and more confidence in, and it actually contributes back to how much the taxpayer is able to also fund ISRO in that sense, right? Because if we are able to actually communicate very effectively to the taxpayer as to what is the benefit that the taxpayer is getting, it in fact, it provides a lot more confidence for the taxpayer to tell the government to fund even more, fund 2 times, 3 times, 4 times more that ISRO is already getting.
I agree with you that this kind of efforts on a regular basis are required. Sometime back, I mean, as you rightly said, the economics of India's space program, because being a government organization, every time either the Public Accounts Committee or someone else will ask these questions: what is the benefit of what all you're doing, etc. There was a study commission. This was the economics of India space program. This was done by Professor Shankar of University of Madras, and this is Oxford University Press. This is a book which was published in 2007. This book, I have a copy of that here. Now, obviously, such efforts, this is quite exhaustive things of 312 pages of this book. Professor Shankar is a well-known economist. And later on, as I mentioned, there were 2 volumes which have been brought out by Indian Institute of Applied Economic Research on 2 specific applications. This was in 2013 or 14, which was commissioned by the Ministry of Earth Sciences, because they were also being asked on 2 things. One was on fisheries applications, what all is the benefit. The second one was agromet advisory services, on the basis of meteorological forecast that you make, add agricultural information of what crop, when to sow, at what harvesting, at what stage is it. Is it should it be irrigated? Should it not be irrigated because there is a likely rainfall? Should you apply pesticide? Not. I mean, so agriculture information plus the meteorological information, agro-meteorological advisories, not at very large district levels, but at a group of villages level to the farmers through the mobile. So this activity they had taken up, and they had done it for a large number of villages. In fact, one of the industries, ITC, Indian Tobacco Company was also involved in it. That report is also available, how much it was useful to the farmers, whether they could, etc. But a much larger canvas of such activities is required. But all these require a certain amount of provoking or certain amount of nudging from I don't know who, but somebody has to do this in order to make people, because some IIM professor or anybody else, they will not, I mean, the economists who are there, who on their own, they will not do. Whether ISRO should uh, commission such things, which they should be doing, or somebody else should be doing. But there is a need for such a thing, so that when this information goes down to the much larger section of people, then they will start, okay, I think this is worth doing, worth spending money on. So efforts have been there, but I think more efforts of this kind are required. And if I'm not mistaken, such things are done in the US. There are many studies of this kind, etc. done. Even the industries do that there. Consultancy programs, they do such kind of things, so that it spurs the activities of industries. So yes, I agree. There is much more of this kind which requires to be done, because by beating our own drum alone, we don't we necessarily don't convey the message. So somebody else has to tell that this is important, or this has helped in this way. There have been some, but much more needs to be done of that kind.
And one of the interesting, again, aspects on the end user side is this emergence of smartphone into
Yeah.
a normal Indian's hand, right? So normally, I've read some of those papers that you mentioned about, including the ones from fisheries and so on. And I see let's say, even a bureaucratic fix that the system has when it comes to what I would call as G2, G2C applications. Because, for example, if the Fisheries Survey of India needs to be brought in from ISRO to connect to the fishermen community, there is a G to G2C kind of model where you have a government entity talking to a government entity, then talking to a citizen in that sense. And there is a possibility of using now smartphones for ISRO to provide end user applications directly to citizens, and to build citizen facing apps that citizens can directly use without any other institutions being involved, to directly pass on the benefits to a citizen through some remote sensing applications that are there, right? So it could be, for example, in this fisheries case, where all of this PFZ information or any other information could be transmitted through Android apps or so on and so forth. There may be some other apps like this that can be used by some other communities, for sure, in remote sensing in all of this. Do you see this as a trend? Do you see any work being done on these front? How is the rollout of certain applications and all of these?
Yeah, there is a lot of work being done today, I find, on citizen-centric science. It is a general term. And I found that some apps have also been developed. One of our institutions, Indian Institute of Remote Sensing at Dehradun, where a lot of this academic work goes on, they have developed necessary applications, and they use this Bhuvan platform. And with the smartphone, any user, etc., who has this smartphone, he collects whatever information that goes on to that platform, and it comes back to the people who are there. For example, in many of the disaster situations, including Kedarnath disaster or any of the other things, etc. So these smartphone-based apps have been used in many of these things, particularly in case of disaster-related applications. They have been used. But obviously, there is a scope for increase of those things. But, there is also nowadays more and more tendency that ISRO need not do everything. So there are many states themselves do such a work using smartphones. There are other organizations which are doing. So particularly, I am familiar with the Indian Institute of Remote Sensing at Dehradun. they have been doing, and also the National Remote Sensing Agency with their one platform, they have developed some of those softwares which are used with the smartphones. Now, this institution which I told you, the Bahal Nobis National Crop Forecasting Center, which uses these people, farmers, and using their smartphones to give them the information on the crop health or any of those things to them. They also use this kind of applications, etc. So there is a growth of this kind of work in the country.
So
yeah, please.
Sorry, I'd say if, we've had a conversation for 2 hours. Thank you so much for sparing so much.
No, it's an opportunity for me also to express myself. I may not have said everything that I wanted to say, or it's quite possible, because this is, in all these things, you forget a few things, whatever comes to your mind. And now that from my active career, which was there till 2012, so it's 8 years which have passed. So obviously the scenario also has changed considerably, but I'm quite familiar with the way we evolved. And the way we evolved, and there the emphasis, as I mentioned, was always on making sure that technology development is not for the sake of development alone, but to ensure that it is useful, and it is useful at the ground level. So that was our emphasis, and to a large extent, we succeeded in that, and that is why we were envied applications program, particularly remote sensing applications program, for quite some years. Thank you very much.
Yeah, so one last final question maybe before I let you go. So do you think that, let's say, ISRO missed the bus on any technology or any initiative when it comes to remote sensing, when you look back at your own career?
I think this is a very difficult question to answer, because any organization, what happens is the priorities are based upon on that day's requirements, etc. And there are two aspects. One is capacity, other is capability. Capability might exist for a much larger activities, but capacity, if it is not there, then you will take up those which are more challenging at that particular point in time, which it can do, and which we can also, the government, whoever is supporting that activity. So in the process, something else might get less emphasis, or so on and so forth. So these things happen in organizations. But to me, to comment on whether ISRO missed this or not, because of what, I think it would be very, it is neither possible to answer, nor it is right on my part to say.
Right. So again, thank you very much for taking so much of your time. It's been extremely valuable. Your insights have been extremely valuable. I think, many of the people who are listening to this podcast, I think, can reflect back to a career of 50 years, trying to do a lot of these things. So I'm sure that, people who are trying to do new things now can reflect back a little bit and see where they stand and, whose shoulder they stand on.
Yeah, thank you so much.
Thank you for staying until the end. The NewSpace India podcast has recently started a Patreon account in order to collect your support to produce a documentary that captures the pioneering work done by many of the generation of scientists during the Sarabhai and the Satish Dhawan era. We believe that this will overcome the gap that none of the institutions in India have gone on to create a documentary-style space history project that captures both anecdotes and personal history of many of the pioneers of that generation. Please do check out the Patreon account and do consider making a contribution that will help produce this documentary. Thank you for your contributions.